Given f of x comma y equals x to the fourth plus y to the fourth minus 2xy, we want to find any relative extrema. The first step is to find the critical points, which is where the first partial derivatives are both equal to 0 or where either is undefined. Once we find the critical points, we'll use the second order partial derivatives to determine the value of d using this formula here. Then based upon the sign of d and the sign of the second partial with respect to x, we can determine whether we have a relative min, relative max, or saddle point at the critical point. So let's begin by determining the first and second order partial derivatives. So for the first partial with respect to x, we'll differentiate with respect to x, treating y as a constant. That would give us 4x to the third plus 0 minus 2y. Then the partial of f with respect to y, we'll differentiate with respect to y, treating x as a constant. So we'd have 0 and then 4y to the third and then minus 2x. So to find the critical numbers, we'll set these equal to 0 and solve as a system, but since we need the second order partial derivatives later, let's go ahead and find those now. So to find the second order partial with respect to x, we'll differentiate this partial derivative with respect to x again, which would give us 12x squared. And then for the second partial with respect to y, we'll differentiate this partial derivative with respect to y again, which would give us 12y squared. We also need the mixed partial of f with respect to x and then y. To find this second order partial, we'll differentiate this partial derivative now with respect to y, which would give us just negative 2. And now we'll use the first order partials to find the critical points. To set these equal to 0 and solve as a system, it's pretty messy, so I did set some of this up ahead of time. So let's take a look. So here are the first order partials set equal to 0. We need to solve this as a system, so we'll use the substitution method. So I decided to solve this first equation here for y. So if we solve this for 2y, we'd have 2y equals 4x cubed. Then dividing both sides by 2, we have y equals 2x to the third. And now we're going to substitute 2x cubed for y in the second equation here. And this is where things start to get pretty involved. When we perform this substitution, we get this equation here where we have 4 times 2x to the third cubed minus 2x equals 0. So if we cube 2x to the third, 2 cubed is 8, 8 times 4 is 32, and then x to the third cubed would be x to the ninth. So we have 32x to the ninth minus 2x equals 0. There's a common factor of 2x here which we can factor out. And now to find the x-coordinates of the critical points, we want to find the values of x that make this equation equal to 0, and that's where 2x equals 0, or when x is 0, or when this quantity here, 16x to the 8th minus 1 equals 0. So for the critical points, so far, we will have one that has an x-coordinate of 0. We'll end up having two more though. To find these two x-coordinates, we have to solve this equation here for x. To isolate the x term, we would add 1 to both sides and divide by 16, giving us x to the 8th equals 1/16. But I wrote 16 as 2 to the 4th, and you'll see why in the next step. If we want to solve this for x and we have x to the 8th, we can raise both sides of the equation to the 1/8 power. But when we do this, notice how x can be both positive or negative, because if we raise a negative number to the 8th power, it would still be positive. So we have to include this plus or minus sign here. So now simplifying on the left, we just have x. And on the right, we'd have plus or minus, well, 1 to the 1/8 is just 1. But when we have 2 to the 4th raised to the 1/8, that would be 2 to the power of 4/8, or 2 to the 1/2. Which we could also write as a square root. So we have x equals plus or minus 1 divided by the square root of 2. So notice how we just found two more x-coordinates for the remaining two critical points. One x-coordinate would be 1 divided by square root 2, and the other would be negative 1 divided by square root 2. And now to find these y-coordinates, we can go back and use this equation here, where y is equal to 2 times x to the third. So using positive 1 divided by square root 2, we would have y equals 2, or 2 over 1, times 1 divided by square root 2 cubed This would give us 2 over 1 times, this would be 1 over 2 square root 2. So simplifying, notice how this gives us 1 over square root 2. And then when x is negative 1 divided by square root 2, the only difference is the sign. So we'd have 2 over 1 times negative 1 over 2 square root 2, which gives us just negative 1 over square root 2. And we can see when x is 0, y would also be 0. So using these critical points and the second order partial derivatives, we'll now determine the value of d using this formula here, and then based upon the sign of d and the sign of the second order partial with respect to x, we can determine whether we have a relative min, max, or saddle point. And again, because of time, I've already done some of the work here. Here are the second order partials from the first slide. So using the point 0, 0, we'll substitute 0 for x and 0 for y to find the second order partial derivative values. So for the second partial with respect to x, when x is 0, notice how this is 0. For the second partial with respect to y, we substitute 0 for y here, which is also 0. So we have 0 times 0 minus the mixed partial squared, which is negative 2 squared, and therefore d is equal to negative 4. So notice here, d was less than 0, or negative. So looking at our notes, that means that at the point 0, 0, we have a saddle point. For the next critical point, we have 1 divided by square root 2, comma 1 divided by square root 2. So for the second order partial with respect to x, we're substituting 1 divided by square root 2 here for x, which gives us this quantity here. And then because y is the same value, the second order partial with respect to y here is the same thing. And then again, we have minus negative 2 squared for the mixed partial squared. Well, 1 divided by square root 2 squared would be 1/2. So this is 12 times 1/2, or 6. And this is also 6, so we have 6 times 6 minus 4, which is equal to 32. So in this case, d is positive, or greater than 0. The second order partial with respect to x was also positive. This was positive 6. So looking at our notes, notice how that means we have a relative minimum at this critical point. And now for this last critical point, it'll almost look just like this, but now the coordinates are negative. But because we're squaring this, we still get 1/2. So this is 12 times 1/2, or 6. This is also 6. 6 times 6 is 36, minus 4 gives us 32. So the result is the same. D is greater than 0. The second partial with respect to x is also positive. So we have a relative minimum at this critical point as well. So for the last step, we want to find the relative minimum function values by evaluating the function at these 2 points. And again, to save some time, I've already done this. Here it is. Let's go and evaluate this. If we raise the square root of 2 to the 4th power, that would be 2 times 2, or 4. So this gives us 1/4. This is also 1/4. And here we have minus 2 times, this would be 1/2. 2 times 1/2 is 1. Well, 1/4 plus 1/4 is 1/2. 1/2 minus 1 is negative 1/2. And now for the second function value, again, the only difference is the sign, but because the exponent is even, this is still going to be 1/4 plus 1/4, and then minus 1. So the result is the same, negative 1/2. And since the question asks us to find any relative extrema, we can say the relative minimum is negative 1/2 at 1 divided by square root 2, comma 1 divided by square root 2, and negative 1 divided by square root 2, negative 1 divided by square root 2. Let's go ahead and finish by looking at this surface in 3D. Here it is. If we rotate this around, notice how we can see the low points on the surface. So these are not only relative minimums, we could also say that they're absolute minimums or just minimums. I hope you found this helpful.